I made a larger version of this sled a while ago and found it very handy for cutting larger pieces of plywood, for cutting long boards in just plain crosscut, or for cutting tenons on the end of long boards, or for cutting dados on long boards. And so being so versatile, I thought it'd be worthwhile to make a smaller version, because 90% of the time I don't need a big sled like that. And so if I'm working with small pieces, like I'm doing here to make some drawers, it saves me having to push a bigger sled back and forth that's heavier, and also easier to lift this small sled off and on the table. Most crosscut sleds are on both sides of the blade, but some advantages of having it on just the left side of the blade is, well, first of all, it's half the size and half the weight. You don't need a back fence to hold it together. And you can use dado blades because they all move in this direction. When there's concern about cutting a piece with a lot of overhang and it may be cracking just before the end, then you can make a simple board with a couple of to fit in there and support the piece. And of course this could be as wide as you want. You might think a disadvantage is having a single runner instead of two runners, but I've made a lot of sleds, some with two runners, some with one runner. And I found that after I go through a season of changes in humidity, that sort of thing, the sleds with two runners do not perform as well as the sled with a single runner. And that's because the base of the sled, the material is moving with humidity, and that's going to push the runners out or pull them together. And so then it either gets too stiff to push or it gets to have a little bit of play in it. A traditional crosscut sled would have a high fence in the middle to bridge the two pieces. But since we don't have that, the fence can be just simple and straight, and that supports putting a T-track on the top. And calibrated flip stops are very handy for cutting to precise lengths without having to measure. And if I want to cut dado, it's very handy because the dados will always come out perfectly perpendicular to the material, and I can use the stop to cut matching dados, say on the sides for shelving. And the scale here will tell me how far the edge of the dado will be from the end of the piece of wood. So I can move along and space the dados every 4 inches or whatever I want. So very fast way to cut dados that are precisely spaced, and be able to do that repeatedly on the next piece of wood so that shelving and things like that line up square and proper. I've got a 1/4 inch wide dado on the saw. Could go any width of dado you want. And I've set the fence so that this block is 1/2 inch from the cutting edge, and that'll give me a 1/2 inch deep tenon. Then I can just slide in my demonstration piece of wood here. So that does a pretty good job with clean shoulders, even all the way around. I'm using teak wood for the runner because it has a very low change in its dimension with changes in humidity. The growth rings are running this way, so therefore I'll use it this way rather than this way, because the change in dimension with humidity in this direction is smaller than the change in dimension with the growth rings. So this direction, growth rings vertical. I'm ripping these to fit snugly in the miter slot. I'll put a link below on how to set the fence precisely in order to do that. And that fits just snug but can still slide. This runner strip is just a little bit thinner than the depth of the miter slot. It needs to be so that it can ride along guided by the edges, not the bottom. So I've put in a piece of cardboard under here to raise it up so it's just slightly above the metal table. I'll apply packing tape. This packing tape will protect the cast iron table from the glue if any leaks out, and I'm cutting away the center part in order to expose the wood surface. Now just make sure the tape is bonded right at the edge. I'm putting on a minimal amount of glue because I don't want to get a lot of squeeze out. Teak wood is a little bit oily, so it's hard to glue to, but on the internet most people claim that Titebond 3 works very well. This is a 1/2 inch piece of MDF, 2 feet by 2 feet, Dimensions don't matter too much. I've got the fence arranged so that the piece of wood is slightly over the blade, and that'll allow me to do a precise trim off when the glue dries. I'll put this weight on to help it clamp. You could also use cans of paint. And no harm done to the table saw. There's a little bit of glue squeeze out here, so I'm just going to scrape that off so that it doesn't cause the MDF to be lifted off the table. I've drilled and tapped some holes going through the MDF into the runner, and I've got 20mm long M5 metric bolts, and that'll just give a little more security on top of the glue in case, you know, there's an impact that would cause the glue to fail. The bolts will hold it in place. I'm just checking that's below the surface. Now I can use the saw itself to trim this edge to be perfectly parallel with the miter. And that leaves me with a perfect reference edge to know exactly where the material placed on the sled will be cut. This step is entirely up to you. I'm going to cut away a portion of the sled that I don't feel I really need, and that'll reduce the weight a little bit. The reason I feel I don't need this is that if I'm squaring up a panel, I'll have good support on the edges that matter against the fence and against the blade. This doesn't really make any difference. And if I'm cross-cutting a long piece here, I've got plenty of support all the way across. I'll make the fence out of this piece of poplar because poplar is lightweight and usually has straight grain and no knots, so good for stability. And here's another trick to make the fence stable. I've ripped it in half, and I'll mark on here the directions of the original piece. Then if I flip one piece over and glue it back together, these arrows are all pointing in opposite directions. So if the piece of wood wanted to go one way, the other piece would pull it back that way. If it wanted to go this way, the other piece would pull it that way. So it makes it much more stable from warping with time and humidity. The fence is 2 3/8 high and 1 5/8 inch wide. I got a bevel on the edge here so that when it's on the base, a little bit of sawdust won't stop the piece of wood from registering against the fence. And on the back, there's a 3/4 inch deep rebate here, 1/8 inch wide, and that receives the track that I've got here. The dimensions of the fence were chosen so that this flip down stop would fit nicely with a small gap between it and the base. So if you're using a different flip stop, you'd probably have different dimensions for the fence. I'm going to screw the fence at one end and then make fine adjustments at the other end to get it perfectly square to the cutting edge. If you can find a screw like this with a smooth shoulder up here, that's ideal for the pivoting end screw. If you can't find that kind of screw, a regular screw will work fine. The fence is held in place at one end by that screw, by the other end by a clamp. I like these Bessey clamps because the clamping pressure force is set by this little bolt and nut, locks it in place. So you can decide the force you want, and then it's the same regardless of the thickness of the material that's being clamped. This clip-on infeed support, which you'll find a link to it below, is helpful when the sled has to be pulled all the way back to start a cut so that it isn't falling off the table saw. I've positioned the fence as square as I can to this edge using conventional methods like a square. And now I'll go to the next level of accuracy using the 5-cut method. The 5-cut method uses a large piece of material cut 5 times in order to magnify the error. And then adjustments are made on the fence in order to reduce that error close to 0. This piece is approximately square, but it doesn't need to be exactly square. I'll mark the edge with the first cut with a pencil line so that I don't lose track. I only need to do a skimming cut on the first 4 cuts. I've got this clamp holding down this corner. I've got this tightly butted against the fence. Now I rotate the piece so that the cut edge goes against the fence. I've cut all 4 sides, so now this rotation brings me back to the very first cut. And instead of a skim, I'll now move over and cut a strip, I don't know, 1/2 inch wide. This strip that was cut off is key to figuring out how much to move the fence. So I'm going to mark it as the back of the saw and the front of the saw because the orientation matters. Okay, the B end measures 0.463 inches and the F end, the front, measures 0.468. This strip is thicker at the front of the saw than at the back, and to correct that, this board would have to be more tilted this way to make that a wider cut, which means this fence has to move this way. The strip that was cut off is 22.5 inches long, and the distance from my pivot screw to the plunger on this dial indicator is 22.75 inch. So I'll use those in the calculation along with the difference between the two measured thicknesses at the ends. 0.468 thickness at one end minus 0.463 thickness at the other end. And I'll divide that by the length of the piece, 22.5, to kind of get the error per inch. You could think of it that way. And then multiply by the distance along the fence, which was 22.75, 3/4 inch, to get the error in the fence. And now I have to divide that by 4 because rotating that panel of wood around 4 times multiplied the error by 4. And that's the amount that I need to move the one end of the fence by to get it perfectly square to the cut line of the blade. Dial indicator set to 0. I know what direction I have to move the fence. It's this way, which I figured out earlier. And I have to move it by slightly more than 1/1000th of an inch. And I think I've got it there. So now I'll repeat the 5-cut method and see whether I've made an actual improvement. .399 on one end, 0.400 on the other end. So 1/1000th of an inch difference along this whole strip. Previously I had 5 1/1000ths of an inch difference along the strip. And keep in mind that this 1/1000th of an inch error is 4 times the actual error. So I've got 1/4 of 1/1000th of an inch error, and I'm not going to do any better than that. Next step is to put a screw from the bottom up into this piece here while the clamp is still applied to secure it in that position. Screw in the middle and a couple more at this end because this clamp exerts some force which might twist the fence a bit. Okay, some extra screws in the bottom. I've got the Kreg top track butted against this block of wood clamped to the fence. I've locked the flip stop to the T-track so that it's 5 inches from the cutting edge when the T-track is in the position I want. So that's where the 5-inch mark on the tape is going to have to go underneath that red line on the cursor. And there's an adjustment screw here, but I'd rather not use it because I've already calibrated this cursor so that this flip stop works on other fences. So rather than having to recalibrate each time, I'm going to calibrate the position of the top track. So I put a pencil mark where the red cursor line is. There's my 5 lined up with the pencil mark. Now I can press this down as I remove the paper backing, and the adhesive holds it in place. Now I can push a piece of wood up against the stop, cut it off. I'll measure it and see if it's exactly 5 inches. So we are 0.02 inches too long. Okay, it turns out the blade from an Olfa knife is the exact thickness I need. So now I can remove this clamp that's holding the top track, insert my shim, butt it up again, and now I've moved the top track exactly 0.02 inches in the correct direction. And we'll do a test to see if that now gives a perfect 5 inch. And I got this kind of clamping arrangement so that I can get the proper downward force on a thin piece. Okay, close enough. And now with the clamps still in place, I can screw the top track into the wooden fence, and that'll lock it in the right position. And trim off the excess fence. The tooth of the blade sticks out far beyond the plate of the blade, and other blades the tooth is really close to the plate. It depends how wide the kerf is and how thick the plate is. And if that's not taken into account, then as different blades are put on, they'll keep cutting away at this defined edge, and then it won't be useful for the other kind of blades. So I made this table which tells me how much shim I have to put between the arbor and the blade in order to get this left edge to come out the same every time. I determined that table by cutting a piece of wood, which each of the different blades, with the same stop position in every case. These pieces were cut with the maximum thickness of shim in place so that none of the blades would chew up the edge of the sled. So each of these comes out a slightly different length. I measured them with digital calipers, wrote the number on the back, and then calculated how much shim would be required to make any of these blades the same as the one with the least amount of teeth overhang, which is the Freud P410. A nice set of shims for this purpose is made by Microjig, and with only 6 shims, depending what combination you use, you're able to move in increments of 1/1000th of an inch from 0.003 up to 0.045, because they've carefully chosen the numbers here that you can use different combinations. The shim goes right on the arbor flange, and that spaces the blade out. In addition, the scale on this top track would be thrown off slightly if I don't take into account the different blades. This knob has to be tightened down pretty good, otherwise it'll wiggle. And I got tired of doing that, so I replaced them with these comfortable knobs that can be tightened without effort. They've got a Rampa threaded insert with the same thread, 1/4 20, a piece of copper pipe, and turned on the lathe.